So in this video, we're going to start by talking about what we call points of concurrency. I like to call them triangle centers because, circles have a center, but does a triangle have a center? So we're going to begin with what it means for lines to be concurrent. So if you take a look at the two pictures on the left side here, those are three lines and they're not concurrent. But on the right side, these three are concurrent. So do you know what it means for lines to be concurrent? It's when lines intersect at the same point. And when we talk about lines, we usually say like three or more lines that intersect at the same point. Because the idea there is that two lines will always intersect, or they'll be parallel. But three lines can intersect in a variety of different ways. When they intersect all at one point, we say they're concurrent, and that point is called the point of concurrency. So that's kind of what we're going to investigate today. We're going to use some Geometry Sketchpad as well. And the first thing we're going to talk about is the incenter. And the incenter is the intersection of a triangle's angle bisectors. So I'm going to open up a Geometry Sketchpad sketch for us really quick. So I have a triangle here, and I'm going to click this button to show the angle bisectors. So each of these segments that come from vertices A, B, and C bisect each angle. And their intersection point is called the incenter. So here's my incenter. And the reason why it's called an incenter is that it's the center of what we call the inscribed circle. A circle that's inscribed as a triangle is inside the triangle and touching all three sides of the triangle. So that's what we call an inscribed circle. So maybe what I'll do is I'll take a screenshot of that. Boom. And we'll drag it in here as a nice little way to look at it. So the thing about the incenter is that the incenter, let's make that a little bit smaller, there we go, is that the incenter of the triangle is the center of the inscribed circle. Pretty neat stuff. So that's our incenter. I want to next go to the circumcenter. So again, I'm going to open up the circumcenter sketch. We'll close out of the incenter one. I want to save it. So the circumcenter is the intersection of the perpendicular bisectors. So these are perpendiculars to the side that go through the midpoints of the sides. It's a perpendicular bisector. So for example, you can see that this segment here that I've just highlighted, it's perpendicular to side AB, and this point right here is the midpoint of side AB. So if I drag this triangle around a little bit, all three of those segments stay perpendicular. And if you notice that all three perpendicular bisectors are concurrent. So let's show that point, the circumcenter. And what's neat about this is that the circumcenter, the intersection of the perpendicular bisectors, is the center of what we call the circumscribed circle. So if we circumscribe a circle, we put it on the outside of the figure. So we can say that the circle circumscribes the triangle. And going back to our last slide, we can say that the triangle is inscribed in the circle. So an inscribed circle and a circumscribed figure, those figures kind of go together. So this is pretty neat, that circle is always going to stay through those three vertices. Pretty neat. And a cool thing about that is it means that the distance from A to G, that's a radius. That's a radius. And because we know in a circle a radius is constant, the circumcenter is equidistant from the three vertices of the triangle. Pretty cool there. Let me close that out. Oh, we want to take a picture of that too. First we'll bang out those radii. Let's delete those. Let's take a nice picture. Boom. Okay, let's window that. We don't want to save it. We'll drag this picture in there. It's way too big. We'll make it small. There we go. And again, the circumcenter of a triangle is the center of the circumscribed circle. Pretty neat stuff. Cool things. Well, let's keep going. This one I think is one of the most fascinating to me. the orthocenter. The orthocenter is the intersection of a triangle's altitudes. So let me bring in my orthocenter. Oops, I didn't want to do that. I want to open it. Here we go. So I have a triangle, and what I want you to notice that I've measured angle BAC. I've measured angle A up here. So as I move this around, and the measure of angle A gets smaller or gets larger. We're going to play with a couple things real quick. So first of all, the orthocenter is the intersection of the altitudes. So I'm going to draw my altitudes, and remember that an altitude is a perpendicular that goes from the vertex of a triangle to a perpendicular on the other side, its opposite side. So it's the height of the triangle. So the segment from A down to BC is the altitude. And as you can see, as I drag this around, it's going to be a bunch of different perpendiculars. And there's our orthocenter. So I'm going to show the orthocenter. Let me hide the altitudes for a second, because this is pretty neat. I'm going to start changing the size of angle A. Right now, angle A is acute. When angle A is acute, the orthocenter stays inside the triangle. But watch what happens when I make angle A a right angle. 87, 88, 89, there's about 90 degrees. Look where the orthocenter landed. The orthocenter is actually on vertex A. It's on the right angle. It's pretty neat. And then if the angle is an obtuse angle, it goes outside the triangle. Pretty neat stuff. But wait, there's more. So what I'm going to do is I have a tool in here. Let's see, I'm going to turn my orthocenter tool on. What this is going to do is it's going to create another orthocenter. So I'm going to make a triangle where one side of my triangle, or one vertex of my triangle, is the orthocenter. And watch where point O is going to be the orthocenter of triangle ADE. When I put it on point C, look where that orthocenter goes. So I made a triangle with the orthocenter inside AC, and the orthocenter is on B. And if I do it again, using maybe triangle ABD, look where that orthocenter is. See it down there? It goes to C. And likewise, if I make triangle BCD, here comes that orthocenter in from the top. And it goes on to point A. So that's pretty cool that if you make a triangle where one vertex is the orthocenter, then the orthocenter of that triangle is the third vertex of the triangle. Cool things there. All right, we'll close that out. Pretty neat stuff about the orthocenter. Oh, let's take a picture of that too. Let's do that. Let's take a quick picture. Bam. Whoosh. Boom. Pop that in, and maybe what we'll do is we'll even take a picture of it when we got that angle A being a 90-degree angle. We'll do 2 pictures on this one, because pictures are cool. All right, let's throw that guy in. We'll make it a little bit smaller. We'll throw that guy in. We'll make it a little bit smaller. So the orthocenter has some kind of neat things going on with it. The last thing we'll talk about, though, is my favorite. It's called the centroid. And the centroid is the intersection of the medians. So let me open up my centroid demo for a second. I don't want to save that. So check out what I got here. What you see is I see triangle ABC, and I drew in my 3 medians. Remember, a median goes from the vertex of a triangle, so from vertex A down to the midpoint of the other side. So F is the midpoint of BC. Now watch what happens when I select median AF. Oh, that's so cool. So my question to you is, how many times larger than FG is AG? Let's watch it one more time. So if you said that AG is twice as big as FG, you'd be correct. Bing, 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 you win. Let's check out another median. Here's median BD. Okay, so it looks like BG is twice as big as DG. Now, what fractional part of BD, what fractional part of the whole median is this first part from the vertex of the triangle to the centroid? Remember, there were 2 of them, 2 out of the 3. That fractional part is 2/3. Pretty neat. We don't want this third median to be left out. So it does that same property as well. So the question now is, what fractional part of CE, the whole median, is the distance from the midpoint to the centroid? And again, we broke into 3 parts, and E to G is one of them. So that fractional part is 1/3. Pretty neat. So we'll take a picture of that too. We love pictures. And let's see where that picture go. Went up here. We'll drag it in there. Let's make it a little bit smaller so we can remember what it looked like. Cool. So let's complete this conjecture. The centroid of a triangle divides each median into 2 parts, so that the distance from the centroid to the vertex is twice the distance from the centroid to the midpoint of the opposite side. I like to also say that this is a 2-to-1 ratio. So the distance from the vertex to the centroid to the midpoint of the centroid is a 2-to-1 ratio. So that concludes our triangle centers: the incenter, circumcenter, orthocenter, and centroid.